welcome to the first ever joint colloquium of the House group and the Utah database group. And the database part is sponsored by Yahoo. It's part of the Yahoo database talk series. Okay? So today we have Daniel from Dincklage from Google talking to us about Yedalog. It's called Yedalog Exploring Knowledge at Scale. So Daniel did his undergrad degree in Germany, Darmstadt, and he got his PhD from the University of Colorado at Boulder. Thanks for coming.
Thanks. I'm Daniel. I'm physically working at Google right now. I'm the current lead for the Yedalog project. So basically today I'm going to talk about this. This is joint work with a lot of other people like Brian Jim, Yedalog, Peter Hawkins, Mark Miller, Francois, Chris Olsen, and Fernando Pereira. Like as you can see, there's a bunch of programming language people here and a bunch of database people here. What we're trying to do is we're trying to build a system that makes it very, very easy for lay users and programmers to explore enormous collections of data. So why do you want to explore data? Well, one of the things that Google does very well is, well, search. And search over the last decade or so has changed a lot. Right? It used to be something we throw up 10 blue links and you click the first one and then there's going to be your answer. At that time, when that was the state of the art, people basically entered keywords in that search box and plussed them and quoted them and you would get basically what you want. These days, actually, people search for very differently. A lot of, you may have noticed this yourself, but when I search, I actually these days enter real queries that I would ask a human. I would enter something like, who influenced Miles Davis? I wouldn't enter Miles Davis and influence as keywords, but I actually enter something like who influenced Miles Davis. And instead of 10 blue links, what Google does these days is actually give you high quality information on the search page itself. So if I ask, if you just type now, who influenced Miles Davis, you'll get basically this thing with one picture slightly different. Which is actually information that goes far beyond anything that's on any page. Because you actually get a direct answer to who influenced Miles Davis. You get actually Miles Davis, you may not be able to read this, but it says influenced by, and then here's a bunch of people who influenced him. And this is not something that Google can find on any one web page, right? There is no page which is the authoritative version of people who influenced Miles Davis. And besides, Google wants to produce this answer for anybody, right? Who influenced, I don't know, Dizzy Gillespie. We want to throw up the same answer. So how do we get this information? How do we know who influenced Miles Davis? Well, the answer is fairly similar to the answer how we used to generate these search terms. Actually, there's a large corpus of sentences, the web. If we parse them, we can, with this web corpus, we can create natural language parse trees. And then we can apply heuristics to it. We can search for sentences that contain the word influence. If we have the natural language parse trees, we can look at the subject and the object of the verb influence, and then if we sum them up all over the web, we can find those instances where Miles Davis is the object of the influencing, and then somebody else is the subject of the influencing, or the other way around. I'm not a linguist, so I might have gotten this wrong. Now the thing here is that this is not an automatic process. There is not a search algorithm that does this for you. There is actually more a human who sits there and says, or perhaps gets the assignment from his manager, we need to display high quality information for the influencing queries. Like, who influenced somebody else? Another query might be, what's the longest bridge in the world? Or, what's the longest bridge in a region? For example, you might also want to ask, what's the longest bridge in California? Now, once that person has that assignment, he or she needs to take this giant corpus of web pages and start extracting the data. Who influenced somebody? What's bridges? How long are they? Right? And how do they do that? Well, they basically take this corpus and do a fairly brain-dead procedure on that. They search for sentences influenced. They count how often does Miles Davis appear? How often does the data look right? How often do I get jumpy data? And then they build a graph and they poke a little bit around. If they're happy with the results, they say, good, this is good. We take this approach for extracting the data from the web. Let's commit this, and then they show it. Okay, so that's basically a way to achieve, a way to get these high quality pieces of information. And and as you can see, the main motivation here is you need to answer a lot of these queries while you're developing your extraction procedure. You need to quickly answer a lot of queries. Who did this? Count me that, and things like that. And it's basically very much a process of rapid prototyping, right? You come up with some idea, okay, I just grab 4 sentences with influence, I look at their subjects and objects, okay, I'll find it. Most of your hypotheses are going to be garbage, going to lead you to evolve something, and you try again until you hit the right thing. Now, the main thing that's going to limit you here is iteration speed. The faster you can do your iteration, the sooner you're going to come up with the general procedure of figuring out who influenced whom just by using web data. And because none of this is hard, right? You can probably come up within 10 minutes with fairly reasonable hypothesis how you can do such an extraction. It's just that you have to do it, you have to validate it, and you have to be sure that your results are good. Now, there's a bunch of other issues here, right? What's also very limiting is that the people who actually do this, they're mostly not programmers, right? I don't know, I barely can distinguish a verb from a noun, so I'm not a good person to do this. So there's actually analysts sitting there and have this as their job, right? And whatever tool they use, it needs to be easy enough for them to use. And last thing is, it's not very important how fast the tool is, because as you can guess, computers keep getting cheaper, right? And humans don't. So from the computer's perspective, the human is getting more expensive at an exponential rate. So we actually can be fairly wasteful in the end in our whatever tool we have, as long as we can come up with the answers quickly. So now you might say, okay, so there's a lot of tools that we have. We have SQL databases, we have NoSQL, we have all kinds of fancy stuff. Why don't we just use that? The problem is that, in my opinion, these tools, they don't really cut it, right? So think about something SQL-based. You can do simple things fairly easily. But could you really figure out complex parse trees and things like that? It's actually going to be really hard, because a lot of this information is going to be highly structured information, right? The documents on your web, they're going to be structured data. They're going to have titles, they're going to have sections, they're going to be tokenized, they're going to be tokenized in paragraphs, sentences. The tokens themselves are going to have parents to link up the parse tree, and it's actually fairly complex data. So with SQL, you're going to be not very happy. Of course, on the other hand, you have the full complexity of something like MapReduce or Flume or stuff like that. But the problem is, this is incredibly tedious. I'm not sure whether you've ever tried to write like something, but if you try something like Hadoop or MapReduce or Flume, you're going to spend there like a few days just to write your first simple job to count how many documents there are. And that is no fun. And moreover, this is not something you can just give to an analyst, right? Because they're not programmers. They're not going to be able to do this. So our claim is, do you need a better tool? Well, our tool is called Yedalog, and it's going to be really much more suitable for this task. So what we promise with Yedalog is that we have a language which makes it really easy to look at structured data. We have a language that makes it transparent where your computation runs. Basically, the tool automatically remotes the computation if it is necessary to remote it. And we also, and in doing so, we supply multiple platforms that can run your program from the smallest set of data, like your 10 records that you have on your local disk, to your multi-terabyte collection of web documents. And and basically, our goal is, it is sort of slightly more complex than SQL to use, but not nearly as complex as Java or C++. So a little bit more on our claims. So first claim, what we claim to improve is we claim we make handling semi-structured data easy. Okay, so think about the following problem. Let's assume you have documents which, and you're looking for documents that have influence as the root of this natural language parser. Well, how is this web document going to be represented? Well, the corpus is going to be first many documents. Each document may have a lot of tokens, and each token will have a pointer to its parent. So let's write some C++ code to do that. Well, this is a fairly trivial task, and already in our slightly cleaned up C++, we wrote 6 lines. That's not good, right? Because this is a trivial task, and we already spent a lot of time writing a bit of code. Because not only do we have to write this, it's also non-obvious, right? You have to check whether the document has a parse tree, because your parse of natural language might have failed. You have to debug those. And in practice, actually, the actual format for storing these web documents is significantly more complex. You'll have to, it's about like 5 or 6 times as much code just to iterate all the tokens. It's fairly now, what we actually, so in Yedalog, this is just a one-liner, right? You say documents, you look at the parse, you look at the tokens, and you figure out that there's an influenced, and you don't, and say that there's a parent. There you go. We want it so that a fairly simple query needs to be a fairly simple expression. So, how do we do this? We basically, Google has this internal representation of semi-structured data called protobus. Our data abstraction is exactly the same as this representation of semi-structured data. And as a result, we have a one-to-one mapping which makes it trivial to do this process. And because Yedalog is based on Datalog, it's based on Datalog, and as a result, we're based on unification and all these kinds of fun things, we immediately get pattern matching on our records. And because of this pattern matching, it is trivial to express very complex constraints on a collection of data, and it's also trivial to synthesize these complex constraints. So we make it easy to process. So the second claim is it's actually hard to mix parallelism and data parallelism and computation.
Are you going to show us an example of how you would have done that other query with a protocol?
This is, yes. Yes, so this is just the intro. Just like a minute or two. And then I'm actually going to talk about the language. So second claim is we make it actually easy to mix parallelism and computation. Why is this necessary? If you think about how you're going to process your multi-terabyte collections, you need data parallelism because you are not going to process these terabytes on your local machine. You need to process it on thousands of machines if you actually want to get somewhere. Now, one problem that basically all systems have that are out there is they distinguish between the language that you use to express your data parallelism and the language you express your computation. And this is very annoying because if you ever decide to move something between one domain and the other, you basically got to rewrite it. Think about if you have basically a language like Flu, where you have data parallel operators combined with Python, or Java, or C++. So once you have written your program, you have basically committed yourself to one expression of this data parallelism. If you now want to change something, you need to rewrite the serialization, or something like that. You will need to seriously change your code. Now with our stuff, we basically do both things in the same language. We basically express everything as a relation. We express our data as a relation. We express our computation as a relation. The user is not aware of the difference between these two kinds of relations. And our tool just sorts it out where everything lies. And in the way, and it works. Last problem, scaling. Scaling is incredibly hard. You write your tiny little program on test data, you debug it. Okay? Well, then you can run it on perhaps a gigabyte of data. Once you run it on a gigabyte of data, you might now want to scale it up, okay? 100 gigabytes. Well, now you've got a problem, right? Either you copy all 100 gigabytes to your machine, let it run over the weekend, which is probably what you're going to do, because you don't really want to rewrite it to run over a network. Because that's hard. Now, suddenly you have to deal with clients, servers, network communication, all that kind of stuff. Or you have to deal with a library like Flu, right? And that's not fun, because you get to rewrite basically your program and debug it all over again. And that's an incredible problem, because if you use a language like C++ or Java, you can't scale. And what we basically do is, because we have this ability to hide both computation and data in the same language, we are free to compile the same operations into completely different backends. We can interpret everything locally, or we can compile it to an aggregator tree for large interactive queries, or we can compile it to something like MapReduce. And that way, the same program that you wrote can scale without any change. So now this is for the claims, and now I'm actually going to talk about the language. Any questions so far?
So,
Yes.
just clarifying questions. So you mentioned the purpose is to allow some users to take as input a large collection of protobuf data
Yeah.
generated from maybe web crawls, maybe something
Yeah.
else, and do some analysis on top
Yeah.
of that.
Yes.
Okay, and you wanted to kind of both run it locally and remotely, but you could, can't you just like, even if you do go straight to something like Flume, have like the option of debug mode, you're running it locally, and then non-debug mode, you're actually launching the cluster.
Well, so basically what you're saying is, okay, so if I were to write a C++ program, I could just write it in Flume, and then I kind of run it with Flume on locally and try to debug. Right? So there's, in our view, there's two problems with this. First, or actually three problems with this. First, you have to write it in something like C++. This is something that only, in my opinion, fairly expert programmers are going to be able to handle. Second, debugging local Flume is not very much fun. I've had to do it when maintaining our backend for Flume. It's actually not easy at all. But third, the biggest problem is that once you have expressed your data parallel operators, you sort of commit to the layout of your program. You sort of say, okay, here I do this join, here I do that join, and you commit yourself to the data structures that you join. And the big problem is if you now decide that you want to move the small computation from this branch to that branch, or you want to move it one hop or so. Because suddenly you need to, moving the computation is easy, but the hard and annoying bit is changing the data representation between the stages. Because you now need to make sure that, for example, you're still stable and that like the hashing works and all that kind of stuff. So basically, yes, you could write it as Flume, but you're not very flexible that way because once you sort of write your Flume job, it's actually sort of fairly tedious to modify. Is that?
That makes sense. My other question would be just before you dive into the details, to take a strategy more like, maybe people Latin as an example, where you still have declarative statements, but you can write entire scripts and you can do many operations on them, and you can still then debug locally and execute remotely.
Yes. Right. Yeah. So that works too. So in so basically, we sort of see this as one step further, right? We want to completely hide from the user what goes on. Right? The user should not have to do any changes and should not need to worry at all about the execution strategy. And so that's, I think, the biggest difference that we sort of have. Is that? Okay. Good. Okay, so now I'm going to talk a little bit about Yedalog. So what's Yedalog? Well, in the basics, Yedalog is a weighted data log. So what's a weighted data log? So here's a very trivial data log example. I'm just going to go over it very quickly. So and explain the individual bits in more detail. So first, we have a bunch of words, like to be or not to be. It's just a list of words, like a vector or something like that. And then we have a small predicate, count. What does this count do? It basically, it takes each word from our list of words, puts it in a variable word, and adds one for every different word it sees. So these parameters here are sort of the group by for the database people here. And in the end, you get a list of every single different word, complete with how often it appears. So this is basically the idea. We express your program as a fairly concise declarative statement in a data log. So how does this allow us to actually do something? So here's our running example. Again, our influential jazz musician. So we have our parse tree here with Ellis was influenced by my status. We have a root token, influenced. We have a passive subject, Ellis. And we have an object, my status. And what we're trying to do is now we have a corpus of web documents, basically with sentences, some of which look like this. And we want to find our influential jazz musicians. So what are we going to do? First, as in every programming language, we've got to load the data. I'm going to use that to explain a little bit about how the programming model works, how the data model works. We then look at our parse trees, find the tokens influenced, find the children of these, we count how often everything appears, and then we revise our example. So first of all, the data model. As I was saying earlier, everything in Yedalog is a relation. So think about it this: we have a file foo.csv. It has 2 columns, k and v, with 3 lines. Lines are ABC and foo formats. You can, if you just look at this file in Yedalog, you can just ask, list me every KV pair in file, and you're going to get your answer with your 3 pieces of data. Fine so far? Any questions?
So does it remove duplicates if let's say V has 3 foo bars?
By default, we have multi-set semantics, so it will not remove duplicates. But you can ask for duplicate removal if you want.
Okay, but that's a way to only get 1 column in the one.
Yeah. Sorry?
How would I get only the second column with this?
Oh, if you only want the second column, you just remove the k and replace it with an underbar. The underbar is basically an anonymous variable and says throw this away.
Oh, so the position is important here?
Well, think about this as a two argument function. Right? Just like a function in C++ with 2 positional arguments, this is a function with 2 positional arguments, where the 2 positional arguments correspond to the columns in your CSV file.
Oh, we have column names, so we can refer to those column names. So basically, file v, k.
Okay, so this is a limitation of my example. Actually, these should be named arguments. Yes. In practice, these are going to be named arguments. Now, what's also a relation is computation. So now, for example, if you think about something like a plus b equals c, well, you can think about this, for example, as an infinite relation of all triples of numbers that sum up to each other. Unfortunately, that's not very practical for a system because infinite things don't tend to work well, as it so happens. So we actually, in practice, what we deal with is we look at everything as a relation constructor. So a plus b equals c it's sort of a thing which we can make into a relation. To make it into a relation, we just need to give it a value for a and a value for b. And then we have a tiny little relation instantiated, which is magically going to contain the value of 3 plus 4, which is 10. And if you then ask our tool for the question mark 3 plus 4 equals c, you're going to get your c is 7. Okay? Questions so far?
Is that a separate relation for every concrete pair of values 3 and 4? Or is that relation just made bigger whenever you see a new pair of arguments?
Neither. The relation never really exists as such at runtime. It's actually more like an iterator interface.
That makes sense.
Okay. So now we need to load our data. Well, in every programming language we need to do that. So we have a load function. We give a named argument path. So this is sort of how you would do your key value pairs in your CSV file with those curlies. Give it a path, file here. This load gives us a value back. This value is a relation. We put it in the variable documents, and then we just evaluate this. And this is going to list us, the individual documents in our file. Okay. So what's going to come out of this? Protocol buffers. So Google has this file format, this format called protocol buffers. It's basically get another structured piece of data. It has basically, you can list them, you can have lists of them, you can have put strings in, you can put ints in, and so on and so on. Basically fairly straightforward structured data. As said, in Yedalog, basically we map our data structures directly onto the capabilities of this thing, because internally every single piece of data at Google is essentially expressed as a protocol. This is the thing you have to be able to write internally if you want to do something. So how is our web page going to be represented? Well, we're going to have a record with a host name. Well, I guess the definition our data came from, perhaps the size of the document we've retrieved, and then we're going to have the tokens of the parts. Each token is going to have. So the tokens are basically a list of tokens, right? For every word in the document. Each token is going to have a text, which is basically the password we saw in it. We have the kind of token, whether it was a subject, a verb, or an object, or something like that. And we have the index in this list of the parent. So for example, parent 2 says that for this token, the second token, it starts at 0, is the parent. So this is influence is the parent of Alice here in the parse tree. Questions? So when we do basically our question mark documents, it's going to start enumerating all the documents that are in our piece of data. Okay. So now, now that we have all our documents, we said we wanted to find those documents where somebody influences somebody else. Well, the first step we have to do is we have to filter out every document that doesn't contain at least one token where the text is influenced. Seems fairly straightforward, so how do we do filtering in Yedalog? Well, we basically start with a small relation, and then you just use the comma operator to express the constraint that you want. So let's we have a small relation P with a positional argument with one positional argument and a value. We can take that relation P, we put the positional argument in X, we put the value in Y, and then we say, only show me those where X is bigger or equal to 2. So if we actually look at our relation, this is obviously going to filter out the one where X is, the result where X is 1. You're just going to see the one with 2 entries. So how does this work for our influence example? Well, it's fairly easy. We just take our document, we look at any token, and we say that the text of this token needs to be influenced. And by doing so, we are going to filter out any document that does not contain at least one token that has the word, the text influence. And for our example document, this is going to succeed because the first token is going to have the text influence.
Where does the I come from?
It's just a variable name. Basically, as I was saying, tokens is a list. And you can think of a list as a relation with 2 columns. The first column is the index, and the second column is the piece of data. So in particular, we have our tokens here. So the token at index 0 has the text labels, and so on and so on. This is useful, for example, if you have 2 parallel lists. Thinking about basically you have 2 lists which basically line up. Because you may want to say the ith entry of the first list has some condition that matches to the ith entry of the second list. Something that would be incredibly hard to do in a system like SQL, which doesn't do any of these levels. Because then you can just use this index here to basically express the constraint. I'm going to show that later.
You can do the same thing in SQL, it's just a join.
I'm sorry?
You can do the same thing in SQL. You just join on the position I.
Well, in things like Dremel, it's actually hard when you flag these away. Because then you're going to do omit if and so on. I mean, it's different, a little bit different in BigQuery, but yes.
Does every, oh sorry, does every relation have this index variable, so that every relation has an order?
It's actually not ordered. It just happens to have these indexes, right? These are just, they might come out in practice in a different order. You're not guaranteed that they come out in the index order 0, 1, 2.
But then how would we oh, okay.
So did they, wait, so were they like imported with when you did the first import, or like if, are you still gonna be able to use these indices and use I even if the user didn't sort of have that in the data initially?
The indices here, basically they come out of the fact that this is a list. Right? Basically think about it like in C++. When you have an array in C++, you can say, give me the 0th element of the array. Give me the first element of the array. And this is basically the same, only that it works, that it sort of works in the other direction, right? This is an array where you get all the indices, and you say which ones you want to keep, right? You say, I want to keep those indices of the array where I corresponds to the element of the array where the text is influenced. Does that make sense?
So it looks like an any here.
Yes.
So maybe do other things like all or five.
Yes. I'm going to talk a little bit more about these things in a second. Yeah.
So basically, you're just saying that for any array, you automatically convert the array into a relation that contains a column named index.
Yes.
So do you have an index column for every relation or just for
Um,
array?
Not for every relation, but for a lot of relations. For example, another thing you might consider is a map, right? A map also has keys and values.
Sure.
And similarly, that will have keys. But that's basically it in terms
I
of.
mean, then like in this data model, you have two different kinds of relations. One relation with index, without. So
It's actually not different, right? Because this is just a particular element position. This is just a particular, this index is not special in any way. It's just, under the hood, it's just another argument. I'll explain afterwards. I can show, there's nothing, the index is not in any way magic code. Okay, so now we have, so now that we have our query here, we might want to expand this a little bit. So how we're going to do this, we're going to do what we do in every good programming language. We're going to declare a function. We basically make a filter docs, move the body of our thing in there before we extend it, because if we have one query that we keep extending, it's going to get unmanageable big. And then we basically, this looks very much like any like a function in C++, right? We have a function body, we have a value that we produce, and we have arguments which currently are empty, right? So basically, Yedalog tries to provide sort of, even though it's sort of usable as a query language, try to provide all the conveniences that you get from any other programming language like C++. So now that we have our function, we need to extend it a little bit. We wanted to find situations where somebody influences somebody else. So now we need to find subjects. There needs to be a subject in our sentence. Well, we basically do the same thing, right? We say, we look at the tokens, and we say that the kind needs to be a subject. This basically says, now we're filtering and finding those documents where there is a token influence, and where there is a token whose kind is subject. Now the important thing, which sort of goes back to the question you were asking for here, is now we have a different index here, right? Here we use SI, because if we had put I here, we would have said that it needs to be the same token that is influenced and the subject, but that's not going to give us any useful results, so we need to use a different variable, because otherwise we wouldn't get any decent result. Okay, so now we have a subject, and we need to do a little bit more. Now we need to join data. Basically, sorry, let me back up a little bit. In addition to the subject, we need to, one of the constraints we wanted to express on our subject is that the subject needs to be a child in the parse tree of influenced. And for this, we need to do a small join. So how do we do a join in our language? Well, again, we can just use the comma operator. You and to join, you basically, the join key is basically the variables common to the both things on both sides of the comma. So if we have a relation P, which we're looking at with whose first argument is X, and we have a relation Q with whose first argument is X, well, it's going to join on X, which is going to give us 2 and 3, because that's the common thing for the join key. Now, the important thing here is the whole set of variables that is common is going to be the join key. What's important here is that Y and Z are different, because that allows us to retrieve any results, because if we had Z on both sides, we would not, there are no entries where both the index and the value are the same, right? The index here for 2 has a different value, and the index here for 3 has a different value, so this wouldn't give us any results. So now how does this look in terms of our example? Well, in our case, we need to say that the parent of this subject is the token we found for influence. And the way we identify this token for influence is it happens to be worked by the position of this token in that list of tokens. So we just say that the parent, that the value of parent for the subject token needs to be I, which is exactly the index of the influence token that we had found earlier. Does anybody have any questions about this?
So, I have a question. I'm just how, like, when will people use this as opposed to using Dremel? Because Dremel also operates on protobufs, right?
Dremel operates on protobufs, but so there's Dremel has a lot of. Okay, so Dremel gets awkward when you need to express complex constraints across repeated fields. Basically, Dremel provides so Dremel provides this flatten and this omit if and so on, and it gets very complex once you want to say something with these things. So when you want to, for example, say find me two repetitions in the same field, in the same, but they're not the same. Then you get into trouble and end up with writing extremely complex queries. Other questions?
Can you express the constraint between the indexes in this case?
Oh, sure. You could, for example, say I is larger than SI, or I is smaller than SI, or something like that. It's just two numbers. You can express any, you can add them if you want. Not sure that's going to give you a reasonable answer, but you could do it. Okay. So now this is a little bit, any programmer now will say, oh, but this looks pretty ugly. So why don't we make this a little bit nicer? Well, we can just use a small pattern match because there's just, this token here isn't yet another record. It's a protocol. So we can just use a pattern match which expresses directly what we want to say. Okay? So now we're looking, this program will basically find us those things where something is influenced, which has a child token that's a subject. And then we can do the same thing to detect the object. Fairly straightforward. Okay. So are any questions about this?
I'm still a bit confused on how the indexes are generated, because previously you had mentioned that the indexes could appear in a different order if we were to run our program again.
Okay. Think about it this way. Let's say you have an iterator through an array, right? You can easily program an iterator that is going to spit out the value of the array at a given position and the position.
Mm-hmm.
That's how it works.
Okay, so the order should always be the same.
Right, but the language doesn't guarantee it because there may be operations that reorder things.
Okay, and then an operator like I greater than SI wouldn't make any sense.
Sure it would, because right, these are different. These would be different iterations. Right. This is these will express different tokens. If you basically say I is greater than SI, for every SI that you find, you will get all I's that are bigger. For example, for SI equals 5, you will get I equals 6, 7, 8, 9, 10, and so on. For SI equals 6, you will get I 7, 8, 9, 10, 11, 12, and so on. Okay? So now we wanted to see how many of these things there are. So now we need to go a little bit into aggregation and grouping. So we have our small aggregation example here, where we basically have just a few words and just count them. Right? For every word, you put it in W, then you ignore W, and you add 1. This is just going to count up the number of words, just like any other query language. Okay? Now, there's an aggregator here, which is basically plus, which basically says, for every argument that you have, add 1. And since there are no arguments in that case, we're going to add 1 for every word. Now, if we, however, we put the W up here, where we now have basically a group line. For every distinct word here, we're going to add 1. So, basically, since 2 appears twice, we're going to add 1 for the two occurrences of 2, and we're going to have and resulting into 2, and then we're going to add 1 for all. Okay, so how does this work in our example? Well, we can just add an aggregator with a plus equals 1 to count how many documents there are where we have this influence defined so far. But there's a little problem, right? In our small data set, we don't find anybody whose influence is somewhere, which is unfortunate. So what do? Well, we try a bigger data set, right? So we had our small data set in our TNT directory. Let's try a 100 gigabyte file. But how does this work, right? Now, previously we had a small file, now we have a huge file. Well, we now need to run this program. Previously, our program ran locally. Now we need to distribute this. How do we do that? It's actually really, really simple. Think about it this way. If you were to identify which parts of the program deal with a large bit of data and which parts of the program deal with small data, it's actually really easy. The only bit of the program that deals with a huge amount of data is this documents here, right? It needs to load the entire bit of the entire 100 gigabyte file, and the aggregator here, and it's summed because it has to sum up. This block here doesn't have to deal with any large piece of data at all, because it gets run once per document that we find. And the document is not very large. So we can do a small refactoring here. We can make a second predicate, count small, which expresses the small computation, and basically extract it from here. Then we reformat it, and we end up like this. So now we have our original program nicely separated between the small computation that is going to easily run on one single node, and a fairly tricky computation which has to deal with a lot of data. Okay, so what do we do with this? Well, luckily enough, as it so happens, these bits of the big computation correspond to exactly those building blocks that we already have in our system, right? The bus equals. That's exactly what we can use in a reducer from a map reduce. Loading the documents is just a data parallel load. And this, invoking the small computation, hey, that's just our mapper. And with this, we can just split up our tiny little program into these two bits and compile it, the very same program that we ran before locally, using a fancy distributed infrastructure.
So are you doing that split automatically?
Yes.
Okay.
Because, I mean, if you think about it, it is really a super mechanical, it's really a mechanical thing, right? Because the semantics of the Datalog language, basically, they are, right, for every document that comes out of this thing, do the following steps. Everything that's going to come out of documents and itself is not a huge computation. It's automatically guaranteed to be small. Right? You know that it is small. You don't need to do anything. You know that anything that depends on it's going to be a small thing that you can push in the map. Yes?
But there could be an extreme case in which you have a single document, which is 100 gigabytes big, and has gazillions of tokens.
Yes?
Do you detect these cases? Do you have statistics?
No, because they don't. We haven't run into them practically. Because basically, I mean, like none of the file formats that we deal with internally, they don't have that issue, right? Because internally these, like there's actually a size limit on these protocols. Like internally, it's not a case that's relevant. I mean, if the data were different, yes, but then we would have to do something. But given the setup, we don't have to worry about that.
So your implicit assumption kind of is anything that comes out of that load operator is reasonable for a single machine?
Yes, it's an assumption, yeah. I have questions. And I mean, perhaps the way to think about this load operation is the document, it actually gives you records, right? Like the things that, each document is going to be one record that we process. It's not going to be a huge collection of data. If it were a huge collection of data, you probably are going to represent it as a file name anyway that you will have to build some out there. Yes?
So just talk about like the input data cannot be too large because there are some constraints on the floor size. But is that possible that if you just kind of load the data from each single machine natively, but then the kind of the aggregation, the computation cost on the aggregation is highly skewed, so that you kind of run into the problem that you have to wait for the like slowest machine to complete for the whole parallel.
I'm not sure I understood the question.
So can you go back to the matter and
Yeah, I think I need to hurry up a little bit here.
Sure. I mean,
So let me just finish and then we can do this later. Okay. So now that we have split this up into our mapper, well, we can just run this on our aggregation tree, right? For example, we can just move the mapper down here. We can run the combiners in our aggregation nodes and everything is happy. We can also map this to Fluent, right? We have from any 2 points to each other. You can then use the same, we can then use the same thing in our in our program to basically express the descendant predicate. This allows us then to identify things where the subject is not the direct child of influence, but a indirect descendant of the influence token. And with that, we actually can then get reasonable results. So much for the language, but there's a lot of more stuff there, right? We have a programming language that makes it easy to work with programming, and so on. But it's also really cool from a programming language perspective. Why is that? Because it makes it very easy to express incredibly complex optimizations that would not be possible in any other in a lot of other languages. Or very hard. So, for example, think about the following problem. Let's say we want to translate something, right? Everybody knows Google Translate. So there is actually a public translation service from Google that you can use. And you just need to do an RPC call to the translate server. You need to say, okay, I have here my English text. I want to translate from English to French. And then you're going to get your French out, translated out. Right? Okay, so now we can run this, run our to French thing on a bunch of sentences, and we get the French translation. Okay, now there's a problem. Latency. Let's assume we want to translate 5,000 sentences. That's going to be a really, really long wait. Because every single time you make one query, you're going to wait 10 milliseconds. And even though 10 milliseconds is not a long wait, 5,000 times 10 is actually not that low, right? You're going to wait quite a few seconds here. If you translate 1,000 sentences, you're going to wait 10 seconds. That's not fun. And if you were to do this in something like C++, this would actually be tricky. However, in our language, the tool can do these can do this better, right? It can automatically do this. Because we have this high-level expression of the program, we can just check all the calls. We can basically intercept all the calls of the translate predicate, buffer them up in a buffer until we have enough. And once we have enough, send a batch of all the 500 translate requests that we have. And once they come back, we proceed with all returns. Because the language doesn't give any guarantees on ordering or execution or something. It just guarantees the same properties that a query language does. There are very few constraints on the evaluation infrastructure that we actually have to obey. We can freely reorder. We can delay executing stuff. Right? The only thing that happens if we delay executing stuff is that any data dependency of the thing we executed has to wait until we stop delaying. But we're free to continue executing other parts of the program. And that's really cool because with that we can do automatic batching optimizations, which are incredibly hard in things like C++, and cause a lot of grief when you have to do them manually. So basically, the way to think about it is, before we have a call, before the transformation, we just get a call. We do the RPC and then we return. What we actually do under the hood is the calls go in a queue. The program stops. Once the queue is full, we send the RPC. Once the RPC is done, we unlock everything that waits on the result of the queue. And immediately we have the batching. And there's a lot of these optimizations and other things that get incredibly easy. Think about things like a pointer analysis. In a language like C++, this is really hard to do a pointer analysis. But in a language like this is trivial, right? Because you basically don't have to worry about anything. It's trivial to write a fairly sophisticated pointer analysis. And with that, you can unlock tons of other very cool optimizations and do extremely invasive restructuring of the program and guarantee that the user will get the same result. But basically, you get to finally do your heart's desire of any fancy optimization that you actually want to do. Okay, so this is all fine and dandy. How does this actually work in practice? So there's one example I can talk about, malware detection. So you will have seen things in Chrome where you get this like red box here, right? Where it says, don't go to this page, there's malware. This is going to crash your computer. Well, under the hood, there's actually Yedalog. What happens is that Google expresses everything as protobufs, right? Web pages, they become protobufs. Windows binaries, they become protobufs. Android binaries, they become protobufs. And then there's Yedalog programs that look at these protobufs and know how particular pieces of malware look like. They look at the signal, I don't know. For example, a signal might be uses the recursive delete directory method or something like that. And if it does so, the Yedalog program issues a doesn't filter that program out, and all the programs that aren't filtered out, they go into the file, and that file goes into Chrome to show they view that web page. And it's actually working pretty well. I think the most surprising result about this is that even though you can write extremely sophisticated programs in something like Yedalog, it seems to be easy enough for analysts to use. Like non-programmers seem to be able to, the language seems capable enough to express very interesting things, but not so hard that it's too hard for non-programmers to use. So people who are capable of using things like SQL can still use this and basically exploit the additional language functionality, which I think is a very, very intriguing result, at least to me. Okay, so what do these malware people do? Well, the main things is they need to write new rules. Somebody deploys a new piece of malware. The malware team has to write a new rule to keep everybody safe. Well, okay, so what do they need to do for that? Well, they first need to know whether the detection rule detects something that is already known good, because that would be egg on our face, right? If we say all these Windows binaries down here are malware. And then once they have run this over enormous amounts of historical data and not found any false positives, then they can deploy this and use the new detection rule online when new web pages, new binaries come in to judge whether these things are bad or not. And key to this is to be able to do this very, very quickly. Right? My favorite example, for example, like a few months ago, there was this Windows SSH binary, putty, and some smart person had introduced a password stealer there, which seems like a smart thing, right? Where are people going to enter their passwords? Well, in an SSH client, so that's a good place. But once that's out there, once that's known, you have to deploy a malware detection rule for that thing as quickly as possible, because everybody who downloads that, they're going to have a problem. Right? And therefore, it's key to have the language and a tool that can do this very quickly. Okay, so anyway, so much for this. We basically have this tool called Yedalog. It's a new Datalog-based language. We're trying to focus very much on making it easy and capable. And one of the big things that we're trying to do is we want to make this really practical and useful. Okay, so are there any questions?